Hello everyone, I hope you are doing well. So in this video, we are going to discuss Geeks for Geeks problem of the day, and today's problem is lowest common ancestor in a BST, and it is an easy level problem. So the problem is very straightforward. It says that we have been given a binary search tree with all unique values, and we have been given the value of two nodes, and we have to find their lowest common ancestor. So before finding about lower common ancestor, we must first understand what is lowest common ancestor, and I'm going to explain everything in this video. So let us discuss what is this LCA first, and then we'll discuss how to find it. So actually there exists a very well-known technique for finding the lowest common ancestor, and that is known as binary lifting. So that is a very optimized technique, and it works in login, right, where n is the number of nodes. So you must be wondering that here it is height of BST, right, height of BST, and binary lifting uses login complexity. So which one is better? Actually, you will realize that login is always better. Why? Because there might be a case like this. There are binary search trees like this, right? All the elements are smaller than the previous element. So let's say this was the first element, 100, then 90, then 80, then 70, then 60, and then 50. So you see all the elements are being inserted to the left, and it will form a structure like a linked list. So in this case, the height of the binary tree will be equal to the number of elements. So in the worst case, the approach where we are focusing on the height of the binary search tree, it will be equals to O of n. But this binary lifting will always give us log of n. Right. So this is always better, but it is advanced level topic. So that is beyond the scope of this video, because that will not leave this question as an easy level question, right? So this problem is easy, and we are going to discuss a method which is very basic, but whenever you want to study LCA in depth, you can refer to this technique, binary lifting, and it will be very useful to you. So now let us first understand what is the lowest common ancestor, and for that let me just create a binary tree. So if a tree is like this, right, now let me just take two nodes, any two nodes if I take. So if I take this particular node and this last node, and I want to find the lowest common ancestor. So the first thing is common between them. Like this is one keyword, and lowest is one keyword, and ancestor is the third keyword. So these are the three keywords which will help you realize what is lowest common ancestor. So the first thing is that they should be common, right? Whatever node we are pointing to, it should be common in both of them. It should be the ancestor, it should be one of the ancestors. So if I explain you in technical terms, that whenever you go from your current node to the root node, then the ancestor will always lie in the path, right? So for example, if I take this node and this node, so let's say this node is x and this node is y. So x is not an ancestor of y, because if I try to go from y to the root node, I will go here, here, and then here, right? So all the nodes that are lying on this path are the ancestors of y, right? This is one definition of ancestor. Now we have to find an ancestor such that it is common between them, and we have to find the lowest one among them, right? So I hope that you guys were able to understand what is common and what is ancestor. We'll see with the help of some examples what do we mean by lowest, right? So first of all, in this example, when we have taken these two nodes x, let me just erase all of these lines. So let's say now this is x and this is y. So if I want to find the common ancestor between them, what will be the common ancestor? So first of all, let me just go upwards. I'll go to this node, then this node, and then this node, right? From y, I'll go to this node, and then this node, and then this node. So you see, the only ancestor that is common among them is the root node, right? So this is their common ancestor. Now let me just take some other example. I'll take some other example. So let's say now I want to take this particular node x and this particular node y. Now if I try to go to their parent, so this is the ancestor, this is the ancestor, and this as well. For y, this is the ancestor, and then this particular node, and then the root node. So you see, now there are two nodes which are the ancestor or the common ancestors of x and y. So the first node is this one, and the second node is this one, right? So these are the two nodes that are common ancestors of x and y. Why? Because these are satisfying the conditions for common ancestor. How? Both of them are ancestors of x and y, because both of them lie on the path from x to root and as well as y to root. Both of them are common among them because this is also present in x and this is also present in x as well as y. So now we want to find what is the lowest one among them. Lowest one means the lowest hanging one. That means whose depth is the greatest, right? So there are like multiple ways of saying the same thing in terms of trees. So here I want to say that the one which is farthest away from the root will be the lowest one, right? Or which one has the highest depth will be the lowest one. In case you have multiple common ancestors, the lowest one, that is this one in this case, will be the lowest common ancestor. So this is all that we mean by the lowest common ancestor. Now how do we solve this particular problem? So while discussing the definition of common ancestor, we noticed that we have to do something about the path. Because what are the ancestors? Ancestors only lie on the path from root to that particular node, right? Now if I want to find common ancestors, there is one thing for sure, that I would need the path of both the nodes from root to that particular node, right? So let's say I want to write the path of these two nodes, and for now I'll have to number these nodes. So let's say this is 1, this is 2, this is 3, this is 4, this is 5, and this is 6 and 7 and 8, right? So you see, I want to go to x. So x is actually at node 4. So the path from root to x will be 1, 2, and then 3, and then 4. Now I want to go to y. Y is actually denoted by 8, and the path to 8 is from 1, then 2, then 6, and then 8. Right. So these are the two different paths. Now you must have realized that I am only concerned about the common part among them. So now all of these nodes, that is for the node x that is equals to 4, all of these nodes that are present before 4 are the ancestors of 4. Similarly, for node y that is equals to 8, all the nodes that are present before 8 are the ancestors of 8. Now we try to define our definition by adding one more keyword, that is common. So if I talk about common ancestor, then these are the two nodes that are the ancestors of both x and y and are common between them, right? So you see, first I also had 3 and 6 here, but since they are not common among each other, so I'll have to remove them, right? So I'll remove them. Now these are the common ancestors between these two nodes. I want to find the lowest one among them. Lowest one means the node which is farthest away from the root node, or which has the highest depth among them. That is the last node in this list of common ancestors, right? So this is all you had to do in this problem. The only task that we are remaining with now is how to find the exact path from root to that particular node. But for now, you know that if you know the path, then you will be able to find the lowest common ancestor, because the lowest common ancestor will be nothing but just the node which is common among them. How? You will take the common ancestors among them, or the common values among them starting from root to that particular node, and the last among those common values is the lowest common ancestor. So if the list was like this, 1, 2, 3 and 1, 2, 3 as well. So let me just take one more example. So if I talk about x is equals to 4 and y is equals to 5. So the path from 1 to 4 is 1, 2, 3 and 4, and the path to 1 to 5 is 1, 2, 3 and 5. Now in this case, you will see that these are the common ancestors among both of them, 1, 2, 3. Right. So what will be the lowest common ancestor? It will be 3 in this case. Right. Let me just take one final example, and that will be, let's say I want to consider this particular node. So we have considered till 8. Let's say this is 9, this is 10, and this is 11. So I want to find x is equals to 4 and y is equals to 11. So what is the path from 1 to 4? That is 1, 2, 3 and 4. What is the path from 1 to 11? That is 1 and then 6 and then 10 and then 11. So 1, 6, 10 and 11. Right. So you see that this is the only common node, and this will be the lowest common ancestor. So we have to first find the path from root to that particular node. Once we have found the path, we just have to check till how long they are having the same elements. For example, these 3 elements were same, we have to print the last node among them. These 2 elements were same, we have to print the last node among them. And this is how you can solve this particular problem. And it is guaranteed, and that in the worst case, the root node will be at least common, because the traversal will obviously start from the root node. So if you are regularly watching these videos, then you must know that a few days ago, we had a problem of kth ancestor. Right. So this was one of the problem of the days where we had to find the kth ancestor. Now in that particular video, I used a method using maps. right, where I store the parent of each node and I am able to find the kth parent of each node. So the same method can be used to make the path from a particular node x, then its parent of x, then parent of x, right? And this way I'll be able to reach the root node and I'll have the path from 1 to x. So this is one method, and we're not going to discuss this method in this video. We're going to discuss a slightly different method so that you know what are all the possibilities and what are the different ways you can form your answer. So if you're interested in watching this method, I'll link the video in the I button in the top right corner somewhere here, right? So you'll be able to watch that particular video from there. Now, in this video, we're going to use a slightly different method. We're not going to use any map, or we are not going to use any extra space. We are just going to form the answer in a simple recursive call, right? So how do we do this? So let us first understand in terms of what we can do when we only have one node. Let us not discuss about two nodes. Let us only discuss about one node, right? So let me just draw the tree. So let's say you want to find this particular node, the path from root to this particular node. So first of all, you will have to maintain a vector called path. So this is going to store the total path. Now you will also have to maintain a Boolean variable found. So this is going to store whether the node you are looking for has been found or not. So initially this is empty vector and this is equals to false. Now you just start traversing. Whenever you enter a node, what you will do is you will push back path dot push back the current node, right? You will simply push back the current node into your path, and you will only do it if you have not found your desired node till now, right? So if you have not found your desired node till now, you will just simply push back the current node into your path vector. Now what will happen? Let's say you try to traverse the left half or the left subtree. Now you know that this particular subtree does not have the node that we are looking for. Whenever after traversal, let's say you're just calling those traversal functions in these lines, in these block of code, you're calling those traversal functions. If at the end, if you have not found your desired node in this particular traversal, then you will just simply pop back the element or the last inserted element, that will be the node. If after all the traversals in the subtree of the current node, you have not found your desired node, that means you're just going to pop it back from the path vector. Why is it so? Because if you have not found your desired node in the current subtree, that means this node will definitely not be included in the path, right? So let's say this is node 1 and you started traversing from this particular left subtree. So you pushed back this particular node 2, right? So 1 and 2 are pushed back. Now you go to this particular 3. 1, 2, 3 is pushed back. Now you go to this particular node, that is 4. So 1, 2, 3, 4 is pushed back. Now you come back here, right? Before coming back, you know that you did not find the desired node in the subtree of this particular node. So you will pop back this particular node, right? Now you go to here, let's say this is 5. So you push back 5. You realize that this is not possible because there is no desired node in the subtree of this particular node. So you pop back, right? Now you come back here. So you have traversed all the subtrees of this particular node. So you pop this element because you have not found your answer. Basically what I'm trying to say, if for a node you are not able to find the answer in its subtree, then definitely this node will not be included in the path from root to that particular node, right? So we come back to this particular node 2. So let's say this is 6, you push back 6, then you push back this particular node 7. You realize that the node is not in the subtree of 7, so you pop back this 7. Then you go to, let's say this is 8, then so you write 8 here. Now you realize that there is no desired node in the subtree of this particular node. You pop back and then you pop back 6, and then you know you have traversed the subtree of this particular node 2. You have still not found your desired node, so you pop back from here. Now you come to 1, and now since you have traversed the left subtree, there is no use of it, and we move on to the right subtree. Similarly, we will repeat the same process. But let's say this is 9 and this is 10, this is 11, this is 12, this is 13, 14 and 15, right? So let's say you have traversed the left subtree of 9, right? So you currently have 1 and 9, and now you're going to the right subtree. So you go to node 13 and now you see that you have found your desired node, right? So let me just add one more condition here, that if my node data is equals to what I need, right? Then I'll mark my found as true, right? Or I'll mark my found as 1. Now, when it is marked as 1, you will see that now even if I move to the left subtree, let's say after this 13, I move to this particular 14, right? Now, I will not push it back because I'm only pushing the nodes when I have not found my index or not found my desired node. So this is very important to know. In case of a single node, you can always directly return from here. There is no problem, but you will realize this is an issue when you are trying to find two nodes at the same time. You cannot just directly return from here. Let me just explain this part again. When you are dealing with only a single node, let's say you are dealing with only this node. So as soon as you have found your node, you can just directly return from here. So that way you will never reach these nodes 14 and 15. But let's say you are trying to find two nodes in the same recursive call. And this is the first node that you want to find. So this is, let's say, F1, and this is the second node that you want to find. Let's say this is F2. So if you directly return as soon as you find F1, then you will never be able to find F2. This is a huge issue, right? So that is why in this case we cannot return from here. In this example, what I am discussing right now, we have only considered one node. But remember, we wanted to find the path for two nodes. So that is why we cannot return from here. I'm only explaining with the help of one node because it is easier to understand with the help of one node first, and then you can just simply extend the same logic with two nodes, right? So remember, if you're only looking for one node, then you can return from here. Otherwise, if you're finding for two or more nodes, you cannot return from here, right? So this is the core idea. Now, since you have marked this as found, whenever you use it 14 and 15, you will see that this condition is present, that you're pushing only when that element is not found. So in that case, you will see that these nodes 14 and 15 will never get pushed. Now let's say you have traversed all the subtree of the current node 13. Now you will see that you will encounter this condition, that if not found, you need to pop back the current element. But since you have found your required node, that means you have found your 13. So that is why it will not get popped back. Now you move to the node 9. Right, again you have found your current element, so it will not pop back, and you will move to 1. It is already found, our desired node is found, so it will not pop back, and hence you have the final path 1, 9 and 13. So this is how you're going to find the path from root to your desired node. So now let us have a look at the code, and you will be able to see how we can extend the same functionality with one node to multiple nodes, right? So you see, this is my code, and what I've done is, first of all, I've created two vectors of nodes, path A and path B. So basically, these will be storing both the paths for N1 and N2 respectively. Now I've created two variables, found A and found B, and initialized both of them with false. At the end, what I'm just doing is, I'm calling the traverse function, and let us see what is in this traverse function. As soon as I encounter a null pointer, it means I can just directly return from here. So I have not found the first element, so I'll push back this particular node in the path of the first element, or in this case I'm considering them to be A and B, right? So if I have not found the element B, I'll push the current node in the path of B. So this is similar for both of the vectors. Now if my current node data is equal to the first element that I need to find, that I'll mark, then I'll mark my found A as 1, and similarly for the second element I'll mark my found B as 1. I call my traverse function in the left and the right subtree respectively, and then if I have still not found the first element or element A, I'll pop back the last element from path A. If I have not found my element B, I'll pop back the last element from path B. Right. So this was all about the traverse function. Now I can initialize my answer with 0 and my index with 0. So while my index is less than path A dot size and my index is less than path B dot size. So I just want to find the maximum number of elements that are common in them from the starting. If this particular index of path A is equals to this index of path B, I'll update my answer as path A of index, and since I anyways want to increment my index value, so I am just doing post increment here. So if these two are not equals, that means I have found my first different node, so I can just directly break it from here. At the end, I can just return my answer value, and this would be the final solution of this particular problem. Now let me just quickly submit this and show you that this particular code works, and this solution is absolutely correct. So you see, it passes all the test cases and the solution is correct. I hope that you guys were able to understand the solution. If you guys did, then consider dropping a like on this video, and don't forget to share thoughts in the comments, because your engagement with this particular video really helps the YouTube algorithm to understand that this video is actually helpful for you and to be able to reach more number of people like you who want to keep solving new problems. So I see a lot of people who watch these videos have not subscribed yet. In case you're one of them, then definitely consider subscribing. It's always free of cost, and you can always unsubscribe if you don't find the videos interesting later. So share this channel with your friends. Until the next video drops, keep coding, stay safe, bye bye.